Good morning, all of you. I am Dr. Deepak Yadav, and today we will see one of the complex topic in digital system design subject, that is combinational circuits, and especially we are focused on the adders that we are using in the combinational circuit. So, combinational circuit is the combination of different logic gates in which there is a certain input and the corresponding output are there. So, combinational circuit is a logic circuit that convert the input variable, perform the digital function over them and produce the output correspondingly. So, these are the basic block diagram of this combinational circuit, in which we have the n number of input and m number of output, and there is a combinational logic block over here in which different logic gates are there that can perform the different logical function for the input variable and produce the corresponding output. So, the combinational logic is a circuit that combine the logic gates. Output depend upon the current value of the input functions. So, this is a combinational circuit for which we have to analyze this circuit like with the help of these input variable, we can find the function of the output and finally find out the table. Like in this case, we have the input variable A, B and C and the output F1 and F2. So, if we solve this, analyze this circuit by just putting the output T2, that is equal to AND gate of A, B and C, T1 that is OR gate of A plus B plus and C, plus and these outputs like output of this gate, that is A dot B, output of this gate A dot C, output of this gate B dot C, and this is the sum of all this input combination, that is AB, A dot B plus AC plus BC. So, when we applied this input to this is one of the output as well. This is equivalent to F2, but we have to find F1 as well. So, if we apply this output to the NOT gate, we have to perform F2 bar by using De Morgan's theorem, that is break the line and change the sign, and this combination is added with is multiplied by this and we can find out T. So, T is nothing but it is the multiplication of A plus B plus C multiplied by this F2 bar. Now, this is T3, but we have to find F1. F1 is the combination of T2 plus T3. F1 is the combination of T2 plus T3. So, your T2 is A dot B dot C over here, and T3 is A plus B plus C in multiplication with F2 bar. So, in this way we can find the output function F1 and F2. Now, after finding the this function F1 and F2, we have to make the relationship table between the input variable and the output variable, and this is also known as your truth table. And for the truth table, all the possible combination of input A, B, C are written as this 0, 0, 0, 0, 0, 1, 0, 1, 0 up to 1, 1, 1 and 1, and all the outputs, that is F1 and F2 are written over here, and with the help of these function we have to find out the value of F1 and F2. So, for the input variable A is equal to 0, B is equal to 0 and C is equal to 0, the first entry for the F1 is equal to this. So, if A is equal to 0, this complete term is equal to 0. A plus B plus C is equal to 0, this complete term is equal to 0, this is multiplied by something, but this is again multiplication with 0, so F1 became 0. Similarly, for F2, our F2 is A dot B plus A dot C plus B dot C. So this is 0 into 0, 0 into 0, 0 into 0. It also became 0. So for the first case, the first entry for the input combination of A0, 0, 0 is F0 and F1, 0 and F2, 0. Similarly, we have to perform the same function for 0, 0, 1, for 0, 0, 0, 1, 0 and for 1, 1, 1. And all the possible combination of the output for all the combinations of the input we have to write, and this is known as the relationship table or the truth table. So this is known as the analysis of the combinational circuits, from which we have already a circuit, and we have to find out the statements and the truth table, that is the relationship table between the input and the output variables. Next is, there are few example of combinational circuits as we can see over here. We have the multiple addition circuit like half adder, full adder and BCD adder. Again, the combinational circuit, we have the subtractors also, half subtractor, full subtractors, multiplier, binary multipliers. There is a comparator, magnitude comparator over here, that is we have to compare the which bit is which given number is high. Like if we have the 4-bit number 0, 1, 1, 1 and the another 4-bit number 0, 1, 1, 0, then we have to compare which number is greater and which number is smaller. So with the help of this magnitude comparator, we can easily compare the two numbers and find out the magnitude, which one is greater, or these numbers are equal, or which one is smaller. This binary multiplier, which can perform the multiplication of two number. Multiplexer is a special circuit in which there is multiple inputs and only one output at the output terminal. So if we see the block diagram of the multiplexer, is there is a multiple input and only one output, and the multiplexer selects one of the input to the output with the help of these selection lines. So this is again a combinational circuit, multiplexer. There is another circuit known as decoder and encoders, and there is a code converter which convert the binary codes to the gray codes, gray code to the binary code, or binary code to the BCD code. So these are the some example of the combinational circuit which we are going through in this subject, that is DSD. So how we can design a combinational circuit? So to design a combinational circuit, first of all we have to describe the problem. What is the problem and how we can deal with the problem. So if there is a problem in which there is a certain input and we want a certain output for these input. So first of all we have to decide the number of the input in the problems and what we have to get the output, or what is the number of the output in the circuit. Then we have to make the relationship table or truth table between the input and the output combination for all the possible inputs, for all the possible combination of inputs, and then simplification the output variable which is obtained with the help of this table, and then draw the circuit diagram with the help of different logic gates. So if we take an example of one of the circuits like half adder, it is again a combinational circuit in which what we have to perform, we have to add two bit numbers, we have to add we have to add two numbers of 1 bit, and we have to find the sum, and if there is any carry then we have to find the carry. Like we have the number x and y, we have a number x and y which is a 1 bit number, like this is 1 and this is 0, and we have to add these two numbers with the help of half adder. So 1 plus 0, that is equal to 1, and there is no carry, then your carry is 0. So there is two output, that is sum, and there is a output carry. So if we see the truth table, we have the two input numbers x and y, that is the number of inputs are 2, x and y, and the two output, that is the sum of these two number, and if there is a carry, then there is a carry out of this number. So x, y, sum and carry. Now we have to write all the possible combination of the input over here. So 0, 0, 0, 1, 1, 0 and 1, 1. These are the all possible inputs, and the output for all these possible combination. So if we add 0 in this 0, 0 plus 0 is equal to 0, there is no carry. If we add 0 in 1, then output is 1, there is no carry. 1 0, there is 1, no carry, and 1 1, 1 plus 1 is equal to 0, the sum is 0, and there is a carry output that is equal to 1. Now we have the relationship table. We have to make this sum and carry output. So your sum is this 1 and 2 places, and this is represented as x bar y and x y bar, and this is equal to sum. Sum is equal to as we can see over here, this is the logic function of the XOR gate. So we can write this x XOR with the y as a sum, and for the carry there is one bit only, there is one output only, this is x into y. So your carry out is the x and y. Now we can easily implement this circuit. We need an XOR gate and a AND gate. So this XOR gate represent the sum, that is we have the input x and y, and the sum is represented by x XOR y, and the carry is equal to x into y. The carry is represented at x into y. So in this way, this is the equivalent logic diagram of the sum and carry, and we can also represent this into the by the basic logic gates. So this combination represent the XOR with the help of basic logic gate. So this is the total function of the sum and carry for the half adder. So in this way, we can easily implement any combinational circuit by finding out its inputs and the outputs for all the possible values of inputs. Then we have to simplify the output function, and then implement this function with the help of logic gates. We can find out the combinational circuit for the real problem that is given. So this is the circuit of the half adder. If we want to implement the full adder, we have to add 3 binary bits, like one bit is x, another bit is y, and let's suppose if we have to if we perform these functions before this, it may be there is a carry, that is C in. So this is again equal to 1. So again we have to perform 1 plus 1 plus 1 is equal to sum, that is equal to 1, and there is a carry and carry out. So again we have 2 out, that is sum and carry out. So 3-bit input and 2-bit output, that is known as full adder. We have x, y and C in, or we have sum and carry out. So all the possible of input combination 0 0 0, 0 0 1, 0 1 0 2 up to 1 1 1, and we have the sum and the carry as you can see over here. Now again we have to find out the relationship between S and C out in terms of input variable. So we can find the function this and this 1, 2, 4 and 7. We can also solve this with the help of the K-map, and as we solve we find that sum is the combination of x XOR y XOR z. Sum is the combination of x XOR y XOR z. So if we make the K-map, we find that it is in the first position, second position, fourth position and seventh position. So there is no matching. So all the ones are individual. So if we solve this function, we found the sum is the XOR of y XOR with the C in 3rd bit. Similarly, we can find the function for the C out with the help of these combinations. And now if we have the functions S and C out, we have to implement this function with the help of different logic gates. So this is the gate level representation of your logic function. This is xy, y seen, y into x into seen, y into seen, sum karke, that we find that C out is over here. And for the sum function, it is x XOR y XOR with the z. So this is x XOR y XOR z over here. So this is the representation of full adder in the different logic forms. Now we can also implement full adder with the help of 2 half adder. As we can see, the total sum is equal to x. The total sum is equal to x XOR y XOR z. So we can see over here x XOR y is over here, So if we pass this output to the another XOR gate, we get X XOR Y XOR Z for the sum, and for the carry we have X into Y over here. And if we perform this X into Y with the help of this OR gate, add this into this carry is nothing but X XOR Y multiply by this Z input. So after solving this and adding into this, we get the same function as we get for the full adder for the combination of these logic gates. So if we have the half adder and the another half adder, we can implement the full adder by using these two half adder and a extra logic OR gate. Now binary parallel adder. So if we have the full adder, we can easily add 3-bit numbers. So we can also make an adder circuit which can add two 4-bit number A and B easily. So in the first case, if we write number A over here, number B over here, and initial carry is 0, there is no carry. So if we add 1 plus 1, that is equal to 0, and there is a carry. So this carry behave the third input of the full adder. In this case, this is a carry 1, and these are the two input bits of the number A and number B. So 1 plus 1 plus 1, that is equal to again 1, there is a carry, again another full adder. So we need another full adder over here for addition of 3 bits. We have this 1 and there is no carry, and it is represented as 0 carry. So again there is a full adder. So we need, if we want to add 4-bit number, we need a 4 different full adder. One is over here, another is over here, third is over here, fourth is over here. And in the first full adder, we have to put Cin is equal to 0, as there is no initial carry, it is always 0. So we have the output sum and carry output, as we can see over here. So now we can make this combination in a particular IC package. Like for the first full adder, we have the entries A zeros and B zeros. Initial carry is equal to 0. We get the sum 0, and the output, internal output, is connected to the carry in of the next full adder over here, as you can see over here. The next bit is A1 and B1. It is added again with the C1. We get C2, and the output is S1. Similarly for the next full adder, and similarly for the next full adder. So the total output is, total input is a 4-bit number, as we can see over here, A0, A1, A2, A3, B0, B1, B2, B3, and we get the output S0, S1, S2, S3, and if there is a final carry, which is represented as C4 over here. So this is a 4-bit parallel adder with the help of 4 full adder, and we can convert it into the IC with the help of 7483 IC. This IC is the combination of 4 full adder which can perform 4-bit binary addition of two 4-bit numbers. Now the thing is that for the binary number, we can easily perform with the help of the previous circuit, but if we have the 2 BCD number, then we have to make some correction in the output. Like the first case is that if the sum is less than 9, like sum is less than 9, like if we have to add 2 plus 3, that is equal to 5. The another case is when the sum is greater than 9, because binary is BCD is represented up to the 9. So if the sum is greater than 9, then we have to make a correction that we have to add binary 6 into the result. Another thing is sum is less than 9, but there is a carry is equal to 1. Then again in this case we have to make a correction, that is we have to add binary 6 in the output combination. So we have to add 2 binary 4-bit, 2 BCD 4-bit numbers. One is A0, A1, A2 and A3, another is B0, B1, B2 and B3. So with the help of 4-bit adder, we can perform the initial addition. S0 bar, S1 bar, S2 bar and S3 bar are the result, and there may be a carry out C3 bar. But this is not the correct result, because these are the 2 BCD number. It need to be corrected with the help of if the sum is greater than 9 and in the sum is less than 9, but there is a carry. So to perform this, again we need a 4-bit parallel adder, another IC of 4-bit parallel adder, and in the one input we can directly provide the sum that is generated by this 4-bit number. So in the correction, what we have to perform, if the sum is greater than 1, we have to add binary 6. So we have to design a logic which can perform the sum is greater than 9. So for this, we have to make an input output relationship table for S0 bar, S1 bar, S2 bar and S3 bar, and there is a output Y. So for the combination, if the sum generated is 0, we have to make no correction, so that is equal to 0. For the sum is 1, there is no correction, and up to the point when the sum is 9, there is no need of correction. But after this, if the sum is 1 0 1 0, we need a correction. This is represented by 1, and up to the point 1 1 1, we need a correction. There is represented by 1. So if we make the K map Y for the combination S0 dash, S1 dash, S2 dash and S3 dash, and put these values. So up to the point 9, we have to fill zeros because there is no need of correction, and after this we have to add 1, we have to fill 1 as we need a correction. So if we solve this K map, this is one quad, this is another quad, and for Y is equal to and the output is equal to, this is S0 dash, S1 dash plus this is S0 dash and in this S2 dash, S2 dash. So if we put this logic, we have to make a correction in the output result. So this logic is implemented over here with the help of logic gates. As we can see, there is a AND gate needed, there is another AND gate needed, and there is a OR gate needed. So this is a AND gate, that is S3 bar, S2 bar, and another AND gate S3 bar and S1 bar, which can generate this function Y. This function Y over here. And there is another third case where sum is less than 9, but there is a carry. So if there is a carry, we have to add this carry in this logic also. So the total output is represented by this OR gate, in which this is the condition and this carry is added. Now this output provides the information that there is a need of correction. So if we have the sum over here in the 4-bit combination, the another 4-bit combination is sorted by this. In this way, the outer 2-bit of B input, B0, B1, B2 and B3 are sorted with the help of ground, like 0 over here and 0 over here, and these 2 bits are connected to this output Y, which is only 1. This is only 1 when there is this logic is not satisfied or there is a carry. So this is our shorted over here and over here. So this combination is 0, 1, 1 and 0 and 1, 1 and 0, and this is the sum S0 bar, S1 bar, S2 bar and S3 bar. So your result is now added with this 6 when this combination became 1. So there is an error, and this IC perform the error correction, and we get the corrected output BCD code with the help of these binary combination of these ICs. So in this way we can perform the addition of BCD numbers with the help of different adders. So this is all for today's in the adders. There is another circuit like subtractors, multipliers, which can easily implement by using these basic logic approach for making the combinational circuit. Thank you for today.